In the last video, we learned about these concepts of producer and consumer surplus, two different applications of integrals in a business setting. In this video, we're going to look at a completely different business application of integrals. This is kind of a catch-all section where there's multiple concepts to teach you and they're not necessarily related. In this video, what we're interested in is the present value of a continuous income stream. And I'll explain what I mean by that after I give you a couple of formulas. So these first two formulas here are hopefully things that you've seen before, maybe in a pre-calculus class. The idea here is this is the answer to the question, how much will a $100 investment be worth in 2 years if it accrues interest quarterly at an annual rate of 8%? So what's going on here is you initially have $100, your value of P is 100, but what you're going to do is increase that value to figure out how much it'll be worth by multiplying it by this factor, which represents the interest that you're going to get. 8% interest, so you might be thinking multiply it by 1.08, but that's a little bit overly simplistic because the idea here is your interest isn't just counted one time a year, it's counted quarterly, it's counted 4 times a year. So it's not that you get 8%, you get 2% 4 different times each year. So our value of R is equal to 0.08, but since interest is accrued quarterly, that tells us our value of N is equal to 4. So we take this 8%, divide it by 4, and that's the 2% that I'm talking about here. It's 1.02, not 1.08 that we're multiplying this P by. And you're like, that sounds like a bad deal. I'd rather get 8% than 2%. No, because you're going to get 2% repeatedly. You're going to get it 4 times each year because interest is accrued quarterly. And we're not just looking for 1 year, we're looking for 2 years. So we're really going to end up with 8, this 4 times this 2, of these 1.02s. Anyways, hopefully this is a formula you've seen before. It's nice, it's intuitive. You can kind of follow where all the numbers go. You throw them into a calculator, it spits out some answer, and that tells you how much your investment will be worth in 2 years if it's accruing interest at this rate. And if you have seen this before, the follow-up question was, okay, what if interest wasn't accrued quarterly? What if it was accrued, I don't know, monthly, in which case N was equal to 12? Or daily, in which case N is equal to 365 or 365 and a quarter or something like that. And if your teacher was especially ambitious, they might be like, all right, what if you got interest hourly or every minute or every second? And what you'd see is if you increase these values at N larger and larger and larger, the amount that it'll be worth doesn't continue to get much, much larger. It kind of settles in on some number. This example is supposed to be an early example of limits that students learn before they've ever learned about limits. And really the big takeaway is the limit as N approaches infinity of this top formula, P times 1 plus R over N to the NT, is just equal to this bottom formula, P times E to the RT power. So if instead of compounding your interest quarterly or monthly or daily or whatever, if you're compounding every instant, you're compounding continuously, this formula simplifies to this formula, and it's a little bit easier to figure stuff out. What we do now is we take that same $100 and we'd multiply it by E, Euler's number, that 2.718 that we've seen a few times in this class, raised up to the R times T power. So 0.08 times 2 in this specific case. Anyways, the point is this is kind of a beginner formula, and a more advanced version of it, the continuous version, is the one you see down here in blue. But neither of those are really what we're going to use to figure out the present value of a continuous income stream, because these are both talking about future values and we want present values. But the nice thing is you can use this exact same formula that we have in blue with a negative value at T, and that will tell you the present value for a future payment. What I'm saying is if somebody asked you how much a $100 payment would be worth right now, if that payment isn't going to be made for 2 years, well, what you'd have to do is you'd have to look at the interest rate. Maybe we can assume that it's still 8%. And you'd have to know how interest accrues. Does it accrue quarterly? Or a more real world situation, does it accrue continuously? And if we assume that interest accrues continuously, then we use the formula that we've seen here. But all we have to do is change the T to be a negative number. So we take that $100 and multiply it by E raised up to the negative 0.08 times T. And what we'll see here, if we calculate this value, I guess I should do it, is you get an answer that's a little bit less than 100. If I take 100 times E raised up to the 0.08 times 2, I get 117.35, give or take. In other words, my $100 payment would be worth roughly $117 in 2 years because of this interest. However, if I do that exact same calculation, but make the value of t negative, then what I end up with is only $85.21, give or take. So this answer down here is less than 100. Oh yeah, that makes sense. $100 in the future is only worth $85 right now, because if I had this $85 right now, I could invest it, and with this interest rate in 2 years, it would be worth $100. Similarly, if I had $100, 2 years after that, it would be worth $117. Anyways, the point is, this red formula was supposed to be the most basic version of the formula. But we quickly get away from this formula and into this continuous formula when we consider interest compounded continuously. For the purposes of this video, we don't care so much about future value, so we can take this formula and change it a tiny bit just by adding a negative sign, and then this formula tells us the present value of a future payment. And that's getting a lot closer to what we want here. The only difference between these calculations we did down here in green and what we're trying to get at in this video is we don't want the present value of one payment. We want the present value of a continuous income stream. Because the idea is, if you think in a business context, if you're selling some good and you're making, I don't know, $1,000 a year, for example, you don't get all that money at the end of the year. You get that $1,000 continuously throughout the year. So maybe you want to know the present value of the sales of this product if you know it's going to earn you $1,000 per year continuously over the next 5 years. Well, anytime we're interested in present value of future payments, we're going to need to know the interest rate. So we're told to assume that the interest rate is 3%. So the idea is we're going to kind of use this formula, but not just one time, infinitely many times as the money continues to roll in over the years. How do you change it from one application of the formula to these infinitely many applications of the formula? Well, you involve integrals. We got this same formula, PE to the negative RT power down here, except now instead of P representing a single number, P represents a function, which is why we wrote it P of T. This doesn't mean P times T. This is just function notation to make the point that our payment stream is now a function of time. This is another formula that you can memorize if you want, but if you already knew this formula or maybe this formula, then maybe you wouldn't need to memorize a brand new formula. You'd just be like, yeah, that kind of makes sense. When I think about integrals, I'm thinking about adding up infinitely many things, calculating the total area underneath the curve, and each of those things will correspond with this formula that I already knew. Let's do an example. Our product is going to earn $1,000 per year. What that means is that our function P of T is equal to 1,000. In this specific instant, it's a constant function, but there's no reason it has to be a constant function. In the next example, this will be a non-constant function. The time frame we're looking at is the next 5 years. So we're going to look at the integral from 0 to 5, our variable being time, hence the dt at the end here. What do we want in our integrand here? Our function P of T times e to the negative RT. Our function P of T is just 1,000, and we have to multiply that by e raised up to the negative RT. R is the interest rate, 3%, which is a decimal I write as negative 0.03, and t is just the variable in the problem, so I leave it as a t. If I can evaluate this definite integral, I'll know the present value of a product that'll earn $1,000 per year continuously over the next 5 years if I have an interest rate of 3%. The nice thing about this definite integral is it's fairly easy to calculate. We could pull the 1,000 out in front if we wanted, and then evaluate this definite integral. You might be able to just evaluate this definite integral by looking at it, but in case you can't, you could do a u substitution. You could let u be equal to negative 0.03t, in which case du is equal to negative 0.03 dt. So dt is equal to negative 1 divided by 0.03 du. With these substitutions, this integral becomes 1,000 times the definite integral from t equals 0 to t equals 5. I want to make note of the fact that the endpoints of this integral are in terms of t because I'm switching my variables from t's into u's. In the integrand, I got e to the negative 0.03t, but negative 0.03t is what I'm now calling u, so I have e to the u power. And then instead of writing dt, I could write negative 1 over 0.03 du. The negative 1 over 0.03 is just a constant, so I can pull it out in front of the integral, and I get negative 1,000 divided by 0.03 times the integral of t equals 0 to t equals 5 of e to the u du. Great news about the integral of e to the u du is the antiderivative of e to the u is just e to the u. So this definite integral is just e raised up to the u power evaluated from t equals 0 to t equals 5. If I'm going to evaluate this from t equals 0 to t equals 5, I can't leave a u in here. I have to change my u's back into t's. Now that my variables are back in t's, these endpoints I can just write as numbers. I evaluate this integral and I'm done. I'm a little bit low on room, so maybe I can kind of jump down here. I got negative 1,000 divided by 0.03 times, if I plug in 5 everywhere for t, I get e to the negative 0.15, 0.03 times 5. And then from that I want to subtract e raised up to the negative 0.03 times 0. In other words, e to the 0 power. I got negative 1,000 divided by 0.03 times e to the negative 0.15 minus 1, because e to the 0 power is equal to 1. If you want to leave your answer exact, I guess you'd be done right here, but it's a little bit unsatisfying to stop right here. It might feel like this is a negative number or something. It's not. You might want to get a decimal approximation. To get a decimal approximation, we got to know what e raised up to the negative 0.15 power is. That sounds like a problem for a calculator. E raised up to the negative 0.15 power is roughly 0.8607. So in my parentheses, I have 0.8607 minus 1. And 0.8607 minus 1 is some negative number. What? Negative 0.1303. This negative and this negative cancel out. 1,000 times 0.1303 is 130.3 divided by 0.03. I can go back to my calculator and see that 130.3 divided by 0.03 gives me about $4,343. Wait, what were we trying to figure out again? Oh, right, the present value of a product that'll earn $1,000 per year for the next 5 years. So when you're thinking about how much that thing is worth, you might be thinking it's worth $5,000. But it's not worth $5,000 because you're not getting that $5,000 right now. You're getting it continuously over the next 5 years. And because there's interest on that money that you receive in the future isn't worth as much as money right now. So the present value of this product is not $5,000, although a naive approach might suggest that it should be, but instead it's equal to $4,343. One more example, then we'll call this video and this section good. Example 2 looks a lot like example 1. We want to calculate the present value of a product. In this case, it's a stream of income modeled by P of t equals 10t. So remember up here, P of t was just 1,000. It was a constant function, but it doesn't have to be a constant function. It could be any function that you want, which is why it's written in function notation right here. So in this case, a would be equal to the integral of, this income is coming over the next 20 years, so it'll be from 0 to 20. P of t is 10t squared, so that goes right here in my formula, but that's not the end. I have to multiply that by e to the negative rt power. R is equal to 10%, in other words, 0.10, and t is just the variable t, so I can write e to the negative 0.10t dt. Evaluate this integral, and you'll know the present value of this stream of income. Good news and bad news. The good news is for a lot of students, just kind of pulling the right information out of the problem and knowing the right formula to use is most of the battle. When you get this far, now it's, I don't know, in big air quotes, just calculus. The bad news is this isn't an especially easy antiderivative to take. In fact, you might want to not worry about the definite integral and kind of out to the side, figure out the indefinite integral of 10t squared e to the negative 0.1t dt. Because this is a problem we've actually seen a few times in our class, and it's not easy at all. You got options in terms of how you could figure this out. You might remember that there's one of the tables in the back of the book that will evaluate this for you, but I think what I would do if I saw this thing is rather than try to pull up the book, I'd use integration by parts on this. First, I'd pull the 10 out in front, and I'd say it's 10 times the integral of t squared e to the negative 0.1t dt. And then if I'm going to use integration by parts, I got to think about what should u be and what should dv be equal to. I'm going to let u be equal to d squared, in which case du is equal to 2t dt. And if u is equal to t squared, then what's left in this integral, the e to the negative 0.1 t dt, will be my value of dv. If dv is e to the negative 0.1 t dt, I got to figure out v, the antiderivative of this thing. Figure out the antiderivative of this thing. You could use a u substitution inside this problem, but I bet you're at the point where you don't even need to. Where you're like, the antiderivative of e to the negative 0.1 t is almost just e to the negative 0.1 t, but there's a problem. If you took the derivative of e to the negative 0.1 t, you'd have to use the chain rule. The derivative of e raised up to stuff is e to that stuff times the derivative of that stuff. The derivative of this stuff is negative 0.1. So I'd end up with an extra negative 0.1 right here that I don't want because the coefficient here is a 1. So how do you get rid of that negative 0.1? Well, we'll divide by that negative 0.1. If dv is e to the negative 0.1 t dt, then v is equal to 1 divided by negative 0.1 times e to the negative 0.1 t. Kind of a mess, but we have all the pieces to do integration by parts. Integration by parts tells us that this integral is equal to u times v, so t squared, my value of u, times my value of v. You might be able to simplify this a little bit. 1 divided by 0.1 is the same as 10. So 1 divided by negative 0.1 is negative 10 e to the negative 0.1 t. And from that u times v, I have to subtract the integral of v du. Again, v is equal to negative 10 e to the negative 0.1 t, and du is 2t dt. Good news and bad news. We've applied integration by parts. That's the good news. We've come up with a slightly easier integral to figure out. The bad news is this integral isn't one that we can immediately evaluate. We're going to have to do another step of integration by parts. Let's see if we can clean things up first. We got this 10 out in front that we're going to multiply everything by. In this set of parentheses, I got negative 10 times t squared times e to the negative 0.1 t. From that, I'm thinking subtract, but this negative 10 is a constant and this 2 is a constant, so I can pull both those out in front of the integral. So I'm pulling a negative 20 out in front of the integral. This negative and the negative in negative 20 makes a positive 20 times the integral of, what's left behind is just this t and this e to the negative 0.1 t dt. This is looking a lot cleaner than the line up above, and if you stare at this integral, maybe you'd be thinking integration by parts. In fact, if you don't want to rewrite everything, we can kind of just grab a chunk of this problem and do this down below in red. We're going to use integration by parts, and playing the role of u will be the t, and playing the role of dv will be e to the negative 0.1 t dt. If u is t, then du is just dt, and if dv is e to the negative 0.1 t dt, then v, as we figured out up here, is just 1 divided by negative 0.1 times e to the negative 0.1 t. Instead of writing it in this form, 1 divided by 0.1 is 10, so I'm going to write it as negative 10 e the negative 0.1 t. With these 4 pieces of information, I can use integration by parts to evaluate this integral. This integral is u times v, so negative 10 t e to the negative 0.1 t minus the integral of v du. However, instead of subtracting that integral, I'll pull the negative 10 out in front, and this negative 10 and this negative right here will make a positive 10 times the integral of e to the negative 0.1 t, that's the v, dt, which is my du. Great thing about this integral is we don't need to use integration by parts again to evaluate it. The antiderivative of e to the negative 0.1 t is something we can figure out. In fact, it's something we've already figured out twice, here and here. Instead of writing the integral of e to the negative 0.1 t dt, what I'm going to write is negative 10 e to the negative 0.1 t power. I'll clean this up just a little bit. I got negative 10 t e to the negative 0.1 t minus 10 times 10 gives me 100 e to the negative 0.1 t. So that's my answer. No, that was just this part of the integral. The whole integral is 10 times negative 10 t squared e to the negative 0.1 t plus 20 times this thing that I got in red. Let's see, 20 times this thing that I got in red sounds like minus 200 t e to the negative 0.1 t if I take this 20 and distribute it to this term. And then if I take this 20 and distribute it to this term, I get minus 2,000 e to the negative 0.1t. Just so I don't have any parentheses, I think I'm going to take this 10 and distribute it through also. So I got negative 100 t squared e to the negative 0.1t minus 2,000 t e to the negative 0.1t minus 20,000 e to the negative 0.1t. So finally, that's my answer. No, that was this indefinite integral. We want to figure out this definite integral. The good news is to figure out the definite integral, you just take the indefinite integral and evaluate it from 0 to 20. So to figure out this definite integral, what I'm going to do is take this answer right here and evaluate that from 0 to 20. Evaluating this at 0 and 20 and subtracting the two kind of sounds like a nightmare, something I don't really want to do. So what I'm going to do is cheat a little bit. What I'm going to do is I'm going to take this function and I'm going to copy it into Desmos. So it's what's pictured right here. And then to figure out what comes out of this when I evaluate it at 0, I just got to know what this height is right here. It looks like it's negative 20,000. And then I got to figure out what comes out of this machine when I put 20 in. So that would be this point right here. And it looks like that's roughly negative 13,534. So I get that this integral is roughly negative 13,534 minus negative 20,000. What's that equal to? Well, minus a negative means positive. 20,000 minus 13,000 is $6,466. My stream of payments that's modeled by this function over the next 20 years would be worth $6,466 in the present day. Does that make sense? Well, I sure hope so, because I don't want to do this again. If you think about how much money your stream of payments makes after 1 year, P of 1 would be 10 times 1 squared, so it's only making $10. In the second year, P of 2, 10 times 2 squared is 10 times 4, is making $40. But if I wait a little while, this thing starts to make a lot more money. In the final 20th year, for example, what this makes is 20 squared, which is 400, times 10. So it makes $4,000. So the amount that it's going to make each year is going to be very different. It makes a lot more towards the end than it does at the start. However, I can't just add up all of these different numbers because there's this really large interest rate, this 10% interest rate. And furthermore, it doesn't really make this $4,000 because it's not paid at the end of the year. It's paid continuously throughout the year. But this kind of gives you an idea. If you added up all these numbers, you'd get something a lot more than 4,000. What would you get? I don't know, like 10, 15, 20,000 maybe. But because of this large interest rate, when you look at its present value, you find that that stream of payments is only worth $6,466 because $4,000 20 years from now with the 10% interest rate isn't worth anywhere near $4,000. Anyways, the point is that this answer might seem unreasonable at first, but when you go back and kind of think about it, I think what you find is that answer is not just reasonable, but it's the correct calculation that we figured out with these integrals, and it's an example of how you figure out the present value of a future stream of continuous income.